So let's start with the log functions. So the derivative of the natural ln of x is equal to 1 over x. But why? It's because you can use this general rule, the derivative of ln u, where u is just anything in the parentheses here on your natural logarithm. And that's equal to u prime, I don't know why I just wrote mu, u prime over u. So u prime is the derivative of whatever is in the parentheses, and then u is just whatever's in the parentheses. So for example, we wanted to find the derivative of, say, ln of x cubed. Well, if we look to our formula up here, that's ln of u. U is whatever's in the parentheses, and then within the parentheses we have x cubed. And then u prime is the derivative of whatever's in the parentheses. And the derivative is the derivative of x cubed. And that is found by you doing the power rule, which we learned in the last video. So x cubed, and then on the numerator here we have 3x, bring the power down, then subtract it by 1. So 3 minus 1 is 2, so 3x squared. And then you can simplify this because 3, and then x times x is up here, and then x times x times x up here. So 2x's cancel, and then you have 3x. Sorry, 3 over x, of course. Right, because cancel, 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 and you get 3 over x. So that's it. For natural logarithms, you just have u prime over u. Next, let's move on to log. And the derivative of log is different from ln. And that's just because ln has base e, right? So the derivative of log with base a, and within the parentheses is u, is u prime, just like in ln, but the denominator here, instead of it just being u, it's u times ln a, where a is the base. And then if you remember, the derivative of ln u was equal to u prime over u, but we know that the natural logarithm has base e, right? And if we put ln e right here, that would just be equal to 1, so we just don't need it. So these are the rules. If you're given log with a base a, and it within parentheses is u here, we have u prime in the numerator, and then the denominator is u times ln of a. Pretty simple. So let's just do a quick example here. The derivative of log base 3, and within the parentheses we have x. And that's equal to u prime divided by u times ln a. What's u? Whatever's in the parentheses. U prime is the derivative of x, which is 1. And we found this from the power rule, right? And then divided by u. What's u? Right here, that's x. And then ln of a. So ln of whatever the base is, and the base is 3, right? Right here, so it's going to be ln 3. So now let's move on to exponential functions. We covered last video that the derivative of e to the x is equal to e to the x. But you have to account for the fact that this is a function within a function, or it's a function that has a function within it. We have our function e to the x here, but we also have x. So that means we have to account for this and use the chain rule. So you take the derivative of whatever the inner function is, and you multiply it by the derivative of the outer function. So our outer function is e to the x, and the derivative of the outer function is e to the x. But we also have to account for our inner function x, and then that's derivative is 1. So times 1, and that's why the derivative of e to the x is e to the x. Right? And we also said that, and this is more apparent if you get rid of 1 and just add any other constant here, like 2. So what's the derivative of e to the 2x? Well, the outer function is e to the 2x, so e to the 2x. And what's the inner function? 2x. What's the derivative of 2x? That's just 2. So 2e to the 2x. Basically, we can generalize this with a formula, so you don't have to just remember the chain rule every time. And that formula can be written out like this. Sorry, I deleted too much there. The derivative of e to the u is equal to, of course it's e to the u, right? But what? Times u prime. Kind of like our ln and log derivatives we just did. We're using u to generalize make a general formula here for these derivatives. We did the derivative of e to the 2x, e to the x, whatever. What about the derivative of e to the 5? Well, you're going to notice that e is a constant, 5 is a constant. So if you try and do this, what's the derivative of e to the u? It's what is e to the u? It's e to the 5th power here. But times what? Times u prime. And if u is a constant, that means we multiply it by 0 here. So this is just equal to 0. So if we have e to some constant, it's always equal to 0. So the derivative of e to a constant, to the power of a constant, is always equal to 0. But if there was some variable attached to that constant, like x, then it's not equal to 0. You have to follow the generalized rule for exponential functions here. So we just found out that the derivative of e to the u is equal to e to the u times u prime. But I forgot to mention that it's also times multiplied by ln e. But ln e is just 1. So we don't really care about it, right? It just kind of disappears from this formula. But what if we had the derivative of 2, you might be saying a constant? No, raised to a variable. 2 raised to the power of x. Now you might be saying, oh, do the power rule here. Well, we can't do the power rule, because is this the derivative of x to the n? No, this is the derivative of a constant to the power of x. And let's define that constant as a, okay? So the derivative of a to the power of u, where u is some variable, is equal to a to the power of u. So much like our exponential rule here, and you might be guessing, okay, so it's probably times u prime because of the chain rule, and you'd be right, so times u prime, but we also need to account for ln a, so we need to multiply it by ln a as well. And we didn't need to do this with exponential functions because it would have been ln e, and that's just equal to 1. But for a constant raised to the power of a variable here, we need to account for it. So let's do an example here. Let's do the derivative of 2 to the power of x. So whenever you see a constant to the power of some variable, do not think the power rule. Think this is not x to the n, so I can't use the power rule. I must use a to the u, the derivative of a to the u. And the derivative of a to the u is a to the u times u prime times ln a. So in this case, a is 2 and u is x. So let's follow the formula. First, we need a to the u. So a to the u is just 2 to the power of x. U prime is the derivative of x, and the derivative of x is 1, so we don't really care about it. So times 1, then times ln a. Now we need ln And then within the parentheses is a, which is 2. So this is equal to 2 to the power of x ln of 2. And that's how you do the derivative of a to the u. Uh-oh, what if I gave you the derivative for 5 to the power of x squared? Now let's remember, this is not the power rule, and we're going to use a to the u, the a to the u rule, which is the derivative of a to the u is equal to a to the u times u prime times ln of a. So in this case, a to the u is 5x squared. So we just immediately write that down, and then we need to multiply it by the derivative of u, and if u is 2x, then that means the derivative of u is, if u is x squared, I just kind of gave it away, that means the derivative of u is 2x, right? So times the derivative of x squared, then times ln of a, and what's a? A is this base here, 5, this constant. So let's simplify. We have 5x squared times the derivative of x squared, so that's 2x from the power rule, times ln of 5, and that's equal to 5 to the x squared times 2x, so let's do 2x, and then ln of 5. And that is our answer. Do not try and do 10x to the power of x squared here, because that would be wrong. We cannot multiply these together. Right? If that 5 was an e, right, you wouldn't even be thinking to do that, right? It's kind of a similar thing here. In summary here, we have the derivative of the natural logarithm, which is ln u, and that is just u prime over u. But it's also multiplied by ln e down here. But we don't care about that because that's just equal to 1, right? So ln e is equal to 1. So next we have that the derivative of log to base a, so a being just some random number, and not e, because if it was e, it would be natural logarithm, log base a, and then within the parentheses we have u. That's just equal to u prime, so the same as ln here, and then u, but also we have to account for this base a here because it's not base e, so that's just multiplied by ln a. 3, we have the derivative of e to the u, and we established that the derivative of e to the u is just e to the u, but multiplied by u prime. This is all because of the chain rule, but you can also remember these formulas. And we also said that the derivative of a constant raised to the power of a variable, so the derivative of a to the u, is just a to the u times u prime from the chain rule, but we also have to account for the fact that we have to multiply this by ln of a. It's very similar to e to the u, but if we multiplied e to the u by ln of a, that's ln of e, and that's equal to 1, just like in this case and this case here. So those are the general rules that we just learned. In another video, I want to go through all of the derivative rules and just run through examples. In this one, I just wanted to do rule, then example, rule, then example. In another video, I'm going to go through like 100 derivatives and just, you probably learn more from that one. So stay tuned for that. In the next video, I'm probably going to be touching on implicit differentiation, and that would be it for derivatives, other than the applications that will come later. So have a great rest of your day. Make sure to subscribe to the channel. Watch another video if you found this one helpful.